Hey, welcome to The Explainer. Today we're diving into one of the most fundamental, kind of invisible parts of any Unix-like system, signals. These are the secret messages that let our programs react, adapt, and frankly, survive when things don't go according to plan. So let's just kick things off with a simple question. You've got a program running, it's chugging along, and then bam, you hit Control-C. What actually happens? How does a program that's deep in some calculation suddenly know to stop what it's doing and listen to you?
Well, the answer is a signal. And honestly, the best way to think about it is like the operating system giving your program a tap on the shoulder. It's a tiny, asynchronous interruption that basically says, hey, you, stop for a sec. Something important just happened that you really need to know about.
All right, so here's our game plan for today. First, we'll talk about why these unseen interruptions are so important. Then we'll get down to what a signal really is. After that, we'll look at the 3 choices a program has when it gets one of these taps. We'll check out the programmer's toolkit, and finally, we'll learn how to master the flow of it all.
Okay, first up, let's talk about the why. Why do we even have signals in the first place? What's the core problem they were designed to solve?
The key word here, the one to really remember, is asynchronous. Think about it. When your program reads a file, it asks for the data and waits. It's all on its own schedule. But a signal, it can arrive at any moment, completely out of the blue, interrupting whatever the CPU is busy with. It's a really basic but super important form of inter-process communication.
So now that we know why they exist, let's get a little more technical. What actually is a signal under the hood?
You might be surprised, but at its heart, a signal is just a number. That's it. The operating system delivers a tiny little integer to a process. Each number means something different. For example, the signal sigint gets sent when you hit Control-C, and sigterm is the standard, polite way of asking a program to please shut down. So where do these signals come from? Well, pretty much everywhere. A hardware slip-up like trying to divide by 0 can trigger one. A software timer you set can go off. Your keyboard obviously can send them. And of course, one program can decide to send a signal directly to another one. So when your program gets that tap on the shoulder, what can it actually do? It's not just a passive victim here, it gets a say in what happens next. It really has 3 basic choices. First, it can just do nothing. In that case, the operating system's default action takes over, which usually means your program gets terminated. Second, it can tell the system, nope, not interested, and just ignore that signal completely. Or third, and this is where all the power is, it can catch the signal. This means it can actually pause what it was doing, run its own special code, and handle the event in a totally custom way. Okay, this is where it gets fun for us programmers. How do you actually make those choices? You use a very specific set of tools provided by the system, known as system calls. To set up one of those custom handlers, you've got 2 main options. There's the classic signal function, which is simple, but it's kind of old news and can act a little weird on different systems. The modern, much more powerful, and frankly, the right way to do it is with sig action. It's the standard, it's reliable, and it gives you fine-grained control, like being able to block other signals while you're busy handling the first one. Now, how do you actually send a signal? Well, you use a system call called kill, which sounds way more aggressive than it actually is. Don't let the name fool you. It's not just for killing things. It's the main tool for sending any signal to another process, whether you want to pause it, resume it, or just ask it for a status update. And here's where kill gets really, really powerful. That one little argument, the process ID, or PID, is like a sophisticated targeting system. You can aim your signal at one specific process, or you can blast it out to an entire group of processes, or even every single process on the system that you're allowed to talk to. It's incredibly flexible. You know, sometimes a program needs to give itself that tap on the shoulder. You could use kill for that, sure, but there's a much cleaner, more obvious way. The raise function. It's basically just a nice, readable shortcut for doing exactly that. And what if you want something to happen later? That's where alarm comes in. It's beautiful in its simplicity. You just tell it how many seconds to wait, and when time's up, your program gets a nice little sig-alarm signal. It's the perfect way to build timeouts into your code. All right, we've covered the basics. Now let's level up. What happens when your program is doing something super critical, like, say, updating a database, and it absolutely, positively cannot be interrupted right now? This is where the signal mask comes in. And honestly, the best way to think about it is like putting on a pair of noise-canceling headphones. A process can tell the operating system, Hey, for the next little while, I don't want to hear about these specific signals. The signals don't get lost, they just line up outside the door, waiting. They become pending. And the tool for managing those headphones is SIG Mask. It gives you total control. You can use SIG underblock to add new signals to the ignore list, SIG unblock to start listening for a signal again, or SIG set mask to just completely swap out the set of rules. This leads to a pretty logical question, right? If you've got your headphones on, how do you know if anyone's been trying to talk to you? That is exactly what SIG pending is for. It lets you take a quick peek at that queue of pending signals to see what's been waiting for you. So let's say your program's whole job is to just wait. Wait for an event. You might think, hey, I'll just use the pause function. It does exactly what it says on the tin. It puts your program to sleep until a signal comes in. Sounds perfect, right?
Well, not quite. This simple idea introduces a classic, super dangerous bug in programming called a race condition. What happens if the signal arrives in that tiny, microscopic window of time after you check for it, but before you call pause? Your program will miss the signal, and it might just wait forever. The correct, robust, professional way to solve this is with SIG suspend. This is the master tool. It does two things in a single, uninterruptible, atomic step. It sets a temporary signal mask and then puts the process to sleep. Because it all happens at once, it's impossible to miss the signal in that critical gap. It's the safe, correct way to wait. So, what's the big takeaway here? Signals are so much more than just a way to stop a program. They are a foundational tool for writing software that is robust, responsive, and resilient. They give you the power to gracefully handle whatever the system or the user throws your way, turning the truly unexpected into something you can actually manage.